Hi everyone and welcome back to physics. This is Mrs. Hutchinson and today we're going to begin our new unit on Newton's laws of motion. And we're just going to talk a little bit about the introduction. What are his first two laws? So Newton's laws, I'm sure you've heard of them all before, but the first one, before we really even get into it, let's discuss what is a force, because we're going to be talking about forces throughout this entire unit. A force is a push, pull, or drag type of motion. It is a vector, so remember when you're dealing with vectors, you have a specific direction, so you have both direction and magnitude. If forces combine, they have to be added using vector addition, or vector unit is our following unit. So I'm just going to tell you that right now, that if forces combine, you have to add them using vector addition. You can't just simply add them algebraically. It all depends on how they're oriented. And the units for force are newtons, which are kilograms meters per second squared. And you'll see where this particular value comes into play when we talk about Newton's second law. But Newton's first law, it's pretty simple. I'm pretty sure all of you have heard of it. An object in motion will remain in motion, and an object at rest will remain at rest unless acted upon by an unbalanced outside force. Basically what that means is if you throw something, that object is going to continue to move unless an outside force acts upon it. So if you throw like a baseball and you're like, well, it doesn't go on forever, that's because the unbalanced outside force, air resistance. Okay, if air resistance weren't there, you could throw that ball and it would just continue to move forever and ever. Inertia. We discussed inertia before. It's the tendency of an object to resist a change in motion. The velocity, speed, and direction tends to remain constant when objects are dealing with inertia. And an object's inertia is directly proportional to mass. This is the major one right up in here. Okay, an object's inertia is directly proportional to its mass. What that means is, say we've got a sumo wrestler. Sumo. I don't know how much they weigh, but let's just say their mass, just because it would be fun, is 300 kilograms. It's hefty. And they're not moving, they're just standing. And then you've got a sprinter. So that sprinter has a mass of maybe, let's say, 50 kilograms and a velocity of 25 meters per second. Which one has more inertia? Well, the one that has more inertia is the one that has more mass. Simply because it's harder to get that object moving, and it takes a lot more effort to get that object to stop. So it's a tendency to resist a change in motion. The more mass you have, the harder it is to change whatever motion that particular object is doing, whether it's at rest and it's harder to get it going, whether it is going and it's harder to get it to come to a stop. So again, inertia is directly proportional to mass. Concurrent forces. Let's talk a little bit about what the heck a concurrent force is. Many people get confused by the term concurrent motion or concurrent forces. It's just simply two or more forces acting on the same object at the same time. I'm not telling you that they're acting in the same direction. They're just acting on the same object at the same time. So we've got a little girl. Here is where you're going to love my drawing. Here's our wagon, woohoo, with a little handlebar. Little girl is pulling a wagon while her brother pushes. So here's the little girl. She's going to be pulling the wagon in this direction, so our force of pull. And here's her little brother being oh so helpful, so our force of push. So both of those forces are acting on the object, the wagon, at the same time. Now, we could have the world's worst little brother. So this little girl, she's pulling, doing her best with Go-Go Gadget arm. So she's pulling here. And then you have her tiny little brother saying, don't you dare. And he's pushing it this way. Both of these are examples of concurrent forces, simply because they're acting on the same object, the wagon, at the same time. So her brother is pushing at the same time that she is pulling. It doesn't matter that they're in opposite directions in this particular example, or that they're in the same direction for this particular example. Both are examples of concurrent forces. To find the result of any combination of two or more forces, because they're vectors, you have to use vector addition. I'm not going to show you that here. I'm going to show you that when we deal with our vector unit next. But what I am going to show you is the difference between a balanced force and an unbalanced force. So let's take a look at balanced forces. Balanced forces act on an object, or forces I should say, are balanced when the vector sum is 0. What does that mean? Nobody even knows. No, I know. I'm just throwing it out there. Basically what that means is if the forces on an object are balanced, that particular object is not going to accelerate. So, balanced forces contain no acceleration. So balanced forces, they have no acceleration. What does that mean? That means that you could be moving in one of two ways. You could be at rest, or you could be moving at constant velocity. These are examples, that's a squiggle in case you're wondering. These are balanced forces, or examples of balanced forces. Now, if you're at rest, you're not experiencing any acceleration. Therefore, because you're not accelerating, your forces must be balanced. If, for this example here, we have a jet flying in level flight at constant velocity, that because it's moving at constant velocity, remember from our previous unit, you're not experiencing any acceleration. Since you have no acceleration, your forces are balanced. Unbalanced forces. They're forces acting on an object when the vector sum is not 0. In other words, you are experiencing an acceleration. So if the forces on an object are not balanced, the object has to be accelerating. So, unbalanced forces, they must be accelerating. For example, a rock in free fall without wind resistance. If we didn't have wind resistance, that rock would go right through the earth, because it's going to be accelerating the entire time that it is falling, because it's experiencing the acceleration due to gravity. Therefore, it's experiencing an unbalanced force. So now what we want to do, let's take a little look at some examples of balanced forces versus unbalanced forces. Let's classify these. So classify them as balanced or unbalanced. A car is traveling at 20 meters per second and the driver steps on the brake. Okay, so we're initially traveling at 20 meters per second. Driver says, nah, we're going a little too fast. Let's step on the brake. Are we experiencing an acceleration here? Yes, we are. In fact, we're experiencing a negative acceleration because we are decelerating. Since we're experiencing an acceleration, any type of acceleration, these have to be unbalanced forces. Bicyclist pedals to maintain a constant speed of 3.5 meters per second. Constant speed means no acceleration. If we have no acceleration, our forces must be balanced. So go ahead, pause the video, try these next three on your own. All right, let me go through the answers. Hopefully you pause the video. Let's go ahead and try them. A chair is dragged across the floor at constant velocity. Constant velocity means no acceleration, therefore it's balanced. Number five. How about we go 3 to 4? Number 4, a plane makes a turn at constant speed. A turn. Remember we said that you're experiencing acceleration when you change direction. Therefore, we're experiencing acceleration. Even though it says constant speed, we're making a turn. These must be unbalanced. That one was a tricky one. I know. And an object is dropped vertically towards the ground. It's experiencing our acceleration due to gravity. If I can spell it right. Therefore, these forces are unbalanced. Okay? So probably the trickiest one was question number 4. It makes a turn at constant speed. Turn, if you change direction, remember, changing direction, that's when we can alter our acceleration. So let's move on to the next part, equilibrium. So remember Newton's first law, if no unbalanced force acts on an object in motion, its motion will not change. In other words, an object with no unbalanced forces is said to be acting in its equilibrium. There are 2 types of equilibrium. We have static equilibrium and dynamic equilibrium. Static equilibrium, when something is undergoing static motion, that object is said to be at rest. So if something is in static equilibrium, that object is at rest with no unbalanced forces acting on it. For example, you sitting in a chair or a book resting on a table. This is a little redundant, motionless, yes. But a book resting on a table, that would be an example of static equilibrium. Dynamic equilibrium means that the object is actually moving. However, if it's in equilibrium, that means that that object is in motion with no unbalanced forces acting on it. Here's our prime example. A car is traveling a constant 55 miles per hour. You set the cruise control. That car is said to be in dynamic equilibrium because there are no unbalanced forces acting on it. You're not accelerating. Since you're not accelerating, you are not experiencing any unbalanced forces. So let's take a look at Newton's second law of motion. I think you've heard of Newton's second law of motion before. Newton's second law states that if an unbalanced force acts on an object, the object will experience an acceleration in the direction of the force. In other words, I'm pretty sure you've seen this equation before. F net equals ma. So remember I was telling you how we would get to our unit of force, what that was actually derived to be. So F net means our net force. Our units of force are said to be newtons. Our units of mass are kilograms, and acceleration, as you know, meters per second squared. So if we wanted to solve for our units of force using F net equals ma, just plugging in our units here, we've got kilograms for where our mass was and meters per second squared for where our acceleration was. So what this is stating is that our newtons equal kilogram meters per second squared. So that's what 1 newton is actually equal to. I'm not really sure why on your reference table they write the formula like this. I typically write it F net equals ma, or just simply F equals ma. So again, it states that if an unbalanced force acts on an object will experience an acceleration, which is true, because again, if we have unbalanced forces, you're experiencing an acceleration in the direction of the force. So let's go ahead and try some examples. Of course, I wanted to show you, why wouldn't I want to show you, in the mechanics section that you have, where you have this particular equation, you do have your A equals F net over M. Here's what all of the variables stand for. I really don't know why they didn't just simply write F net equals MA. It just seems more logical, easier to use, but of course I didn't do this, so that's what we're going to go with. So let's do practice problem numero uno. So here's what problem 1 states. A boy exerts a 14 Newton force on his little sister who is on a sled. So he's not just shoving her for no reason. The sister and the sled combined have a mass of 25 kilograms. At what rate did they accelerate? So again, here's where we do our given, our wanted, our equation, our substitution, and of course our answers. So please make sure that you're doing this because as you can see, we are accumulating a lot of different equations. So it really, really helps. We've got a 14 Newton force. Their mass is 25 kilograms. And at what rate did they accelerate? So here's our given. We've got a net force of 14 newtons. And we've got our mass of 25 kilograms. Our wanted acceleration our equation, it's of course the one we just learned, Newton's second law, F net equals ma. Let's substitute everything in. So we've got 14 newtons equals 25 kilograms times our acceleration. Solving for our acceleration, so dividing both sides by 25, you should get an answer of 0.56 meters per second squared. Make sure you get the units right. I know they're not necessarily given to you in your substitution, but they really are, because again, remember, a Newton is a kilogram meter per second squared. So now you bet you can guess what I want you to do. I want you to go ahead and pause the video and try question number 2 on your own. So here's question number 2. Hopefully you paused the video and tried this on your own. A 2 kilogram hockey puck. It should say hockey puck. I mean, I guess it's just assumed that we're talking about a hockey puck here. Whoa. Bam. A hockey puck. 2 kilogram hockey puck is accelerated by a slap shot force at a rate of 28.9 meters per second squared. What is the force exerted with the stick? So, let's write down our givens. So we've got our mass is 2 kilograms. By the way, that's a really heavy hockey puck, just so you know. Mass is 2 kilograms. Our force, net force, is equal to 20. That's a lie. Pardon me, I should really read. Not our net force. Our acceleration is equal to 28.9 meters per second squared. We're solving for our force. Okay, so now what equation are we using? Probably the one that we just learned, F net equals ma. And let's substitute everything in. So we would get F net equals 25. Holy cannoli. I'm not on a terrible roll. 2 kilograms times 28.9 meters per second squared. That's how you would set it up. If you pay attention, unlike myself, I should really focus. And our answer would be F net equals 57.8 newtons. So hopefully that's what you did. You didn't make as many mistakes as I did on that particular example. It's not too bad. So make sure that you are substituting appropriately with units. Now what I want you to do is pause the video and try question number 3. So here's how we do question number 3. Hopefully you pause the video. A boy drops a 6.5 kilogram rock from the top of a tower. What was the magnitude of the gravitational force that accelerated the ball toward the ground? So, here's what we know. We know a fair bit of information, but there's something hidden in there. So, let's go ahead and write down our givens. We know the mass of the rock is 6.5 kilograms, but that's all they really give us. They do say that he dropped the rock from the top of a tower. Okay, so if you drop something, what is the acceleration that particular object is feeling? Well, that object is experiencing our acceleration due to gravity. And our acceleration due to gravity is 9.8 meters per second squared. This value is found on the front of your reference tables. Remember we discussed it a while ago? It's on the front of the reference tables. It's under G, and G equals 9.8 meters per second squared. That's the acceleration due to gravity. So they do give you that particular information. They just don't necessarily give it to you outright. They say that a boy drops it, so they give you that acceleration. I'm going to show you later on a second equation that deals with our acceleration due to gravity. It's a particular type of force, but for right now, we're going to use Newton's second law. Our wanted is the force. And our equation is F net equals ma. So let's go ahead and substitute everything in. We've got solving for our force, 6.5 kilograms times 9.8 meters per second squared. And final answer, do a little multiplication, we would get our force is equal to 63.7 newtons. Okay. Not too bad. That one was definitely a little on the trickier side, solely because I didn't necessarily give you the acceleration due to gravity. I kind of let you figure that one out on your own. Okay? So hopefully if this made sense to you, you can move on to our next video either today or tomorrow, depending upon how far ahead you might be. So hopefully this makes a little bit of sense. We talked about our inertia force, we talked about, well, our inertia, law of inertia, and we talked about F equals ma. Those are the first two laws that Newton had created. And I hope you enjoyed this video, and I'll see you for our next video.